All right, guys. So, any questions from homework stuff? Yeah.
On section 11.1, there's a word problem.
Which one?
The very last word problem. Yeah, it's
No.
about the triangles area. 120.
In section 11,
Section 11.3.
3. Ooh, I like it. All right, so this is number 120, section 11.3. Oh, today's going to be a good day for running. All right, so I desperately, if you follow the steps on that handout that I gave out a while back, this is a geometry problem, so it's good to draw the picture, right? If you have a problem about a shirt being discounted 10%, draw a shirt. That's not going to do you any damn good. So first thing I'm going to do is draw me a triangle in. There's a triangle. Has an area of 35 square inches, and its base is 3 inches more than its height. So here's the height. Here's the base. So what, in English, what are the parts of this problem? What are the players? A triangle has an area of 35 square inches. Its base is 3 inches more than its height. Okay, you went straight to the thing you got to be careful about, right? You've bypassed a lot of stuff, and that's where people make the most mistakes. What are the two things? Height and base. And it says the base is 3 more than the height.
So height x.
Height is x. That's the important first step. Do not skip that step. Don't do it.
Yeah.
So height is x, and now base is, because you define height to be x. If base is 3 more than the height, and you don't know what the height is, you better call it something so you can write what this guy is. Before I did that, I can't do this. And you can label your little chart. So I got my picture. There's x was 3. There's x. Now what's the last piece that actually is where the equation comes from that I haven't used yet?
The area.
The area. What's the area of a triangle in general? Yeah, right.
1/2 base.
Yeah, 1/2 base times height. And real quick, I don't know if you draw a parallelogram, its area is base times height, right? Base times height. And a triangle is always going to be half of some parallelogram. That's why the formula is 1/2 base times height. Just 1/2 of a freaking four-sided figure, right? All right. So how do I write that? Then the area is 1/2 base times height. What did I tell you the area is?
36, right?
36. 35? What's the base? What's the height? Base is x plus 3. And the height is x. All right. What's a really good first step on this now to solve this? I appreciate that. That's technically what you have to do if you didn't have another side. But if the worst part of that is the 1/2, a fraction is throwing me off, you can just sort of multiply both sides by 2, right? The minute you see a fraction in your equation, kill it if you want to, and I'd want to. So multiply both sides by 2, so that's gone. And you can distribute the x. All right, that's all I'm going to do for you. You can keep going there, right? Now this should be the easy part. But do you see how the step saved you? Draw a picture. Who are the players? Label the picture with what you figure out here. What's the equation coming from? In this case, it was the area that gives me the equation. And once you're there, you forget all this crap and you just solve the equation you made. How do you solve this?
Square root.
No? You can't square. Well, you could after you do a lot. But I could move to 70, equal it to 0. Try to factor it. If it doesn't factor, I could use or sometimes better quadratic formula, right? That should factor actually. Believe it or not. So that's all I'm going to do. That's enough. But I just have faith in the steps. People want to jump straight to the equation. That's insane. You're going to lose something. Or you feel like you're supposed to be able to. Don't. You know, it's crazy. Yeah.
So that would be equal to 0 though. So whatever answer we get, it'd be flipped, pretty much.
Well, not flipped, but you'd have to solve it out.
Yeah. If it's x plus 3, you get x equal negative 3. Since it's a physical thing, of course, it's a word problem, so you got to throw the negative stuff out.
Do you have to plug it in to find the answer? Because there's going to be 2 answers, or no?
Well, if you know x, you know x plus 3. If x is 7, then that's 10, right?
Yeah.
Yeah. Yes?
For 11.3, number 21, do we just plug in this point? So, like, I'm confused.
Oh, all right. Let's say I had a function. And it looks like this. Right, that's the function, that's what it looks like. And I want to know, where's a function 0? Well, can somebody tell me how many times is that function 0?
Once.
Nothing. 3 times? Oh, sorry. It's 3. 3 times its function is 0. Like, what's the function here? Maybe let me make a scale here. Right at 0, what's the function value? 1. At 0, the function value is 1. What's f of 0? 1, because that's where it is. So really, another way of saying, when is the function 0? Another way of saying that is, when does a function hit the x-axis? Because when it hits the x-axis, what's the output?
0.
So f of 4 would be 0, because it's at the 0 point. It's not y equal 1, it's not y equal negative 1, it's y equals 0. It's on the axis. So another way of saying, when is a function equal to 0, which is the question, is what are the x-intercepts? So think about what quadratic formula does. It solves, ax squared plus b equals c. It solves this. It solves that equation, so visually it finds the x-intercepts. So here, do you have to do any work? All the work's already been done for you. You just got to find the answers. You just got to find when is it hitting the x-axis. Cool. I like it. So it's sometimes math is interpreting the question, right?
Yeah.
What's the question? What's another way to say that same question so I can look at it right and do it? How's that? Is that all right? So just remember, quadratic formula is used to solve this equation when it's equal to 0, and that means those would be the x-intercepts if you graphed it, because that's making the output 0. That must be on the x-axis. Okay, maybe. That's why we sometimes call x-intercepts roots of a function, which gets a little confusing, but it's because that's where the roots would start in a plant. That's on the ground level, right?
So in this situation, we mentioned 3 points.
Yes, there would be 1, 2, 3 places where it equals 0. Right? So 4 is one of them, like 1/2 is another one maybe, and whatever the hell that is, -5, whatever. Right? But on your picture they show you, you can see them very easily. Right? Just see where it hits the x-axis. This book does that every now and again, which I like. There's problems where they say, just look at the graph and give me the answer. And it throws us off because you're so used to give me the function. I can solve it. That's beautiful. It brings tears to my eyes. But they give you the picture. They've already done all the work. They've already figured the function out totally. They're just asking, look at what we did and tell us what happened. Anything else from homework? How you guys doing? You alright? My God, it's the last week. Holy crap. They said y'all should get shirts. Y'all should get, I survived. Right. Even if you fail, you're like, I don't care if I fail. I survived the damn thing. 3 weeks. Bam. Alright. So no other questions? Oh.
I think on 11.1, but it says something about finding the distance between 2 points.
Yes, cool.
How would you?
And we talked about, we realized that the distance between 2 points is related to the Pythagorean theorem. So if I have a point there and a point there, how far apart are they? This triangle. And this would be x2 minus x1, and this would be y2 minus y1. If you guys remember this, we thought we can do this very quickly because we did it the other day. So this is maybe side A, side B, and then we call it side D because we want to look at it as a distance now. We're going to call it C. So this would be x2 minus x1 squared plus y2 minus y1 squared equals d squared. So the distance formula is just the square root. That is the official distance formula, and it's got the pieces, parts of slope in it, which sort of makes sense. You guys see the pieces, parts of slope? How much does the y change? How much does the x change? Now they relate to the lengths of the sides. How much does the x change is this side? How much does the y change is that side? Sides of a triangle, Pythagorean theorem. Bam! Right, so very often, sometimes people will remember this formula and forget why it makes sense. It makes complete sense. It's just Pythagorean theorem. A squared plus b squared equals c squared. Now I'm just calling it d for distance. Is that cool? So if I give you 1, 3, and 4, 7, you just plug 4 minus 1, 7 minus 3, square root it. Why do I not put a plus or minus, of course? Because
a negative distance.
Can't have a negative distance, so it freaked me the hell out. Right? That's advanced physics stuff. We're not there. Negative distance. It's in a different dimension. No. Okay. Anything else? Is that good? You guys doing all right? I'm just worried about you. Y'all look a little...
Yeah, I got a question on that.
All right. You look exactly like I expect you to look, actually, but still. You got it? Where are we at?
It's 12.1.
12.1?
12.1, yeah.
Oh, ask me later. That one's extra credit. Remember? You guys know, if you missed out, 12.1.
Yeah.
I did say this, right? 12.1 is extra credit.
Mm-hmm.
Yeah.
Good. All right. 12.1 is extra credit.
Is 10.2 extra credit?
10.2? I don't remember. No. Good try, though. I like that. That's all right. Just hopeful. All right, so very quickly then, a little review of what we did yesterday, and then we're getting into logs today.
What we did yesterday?
You know, in terms of the class. give me so if I had this.
Is log the one that you need the
We'll find out.
calculator?
No, not always. Do you always need a calculator for square roots? No, some square roots you can do. If I said square root of 49, you better not reach for your calculator. But what's the square root of 72 exactly? You need a calculator. Not exactly, but give me an approximation of decimal. You're going to need a calculator for that.
I just remember that
Logs are the same way. Some logs I can do. Some logs I can estimate.
maybe it was tangent. Isn't tangent the one?
Ah, there you go. Then you think on trig, and that's way out of us.
Oh.
Shit.
What section is this?
Say again?
What section is this?
12.2, right? Yes. So, I mean, 12.2 should be pretty straightforward, I'm hoping. The weirdness is we put the variable up here now, so now it's my power that I don't know. It can change. And the resulting graph kind of makes sense if I plug some stuff in. I always plug in some negative stuff. So these are my go-to 5 for any function. I'm not sure what it looks like. Of course, at this point, I know how a lot of functions look. When you plug a negative 2 in for x, what do you get out? Careful. No? What does the negative power do? The negative power flips. So 5 squared is 25, so 5 to the negative 2 power is 1 over 25. It just flips it. Do you guys see that? 3 squared is 9. So 3 to the negative 2 is 1/9. Nothing major there. A negative power, all I can do is flip what you would normally get. So what's 5 to the negative 1? 1 over 5. 5 to the 0? 1. 5 to the first? Crazy. 5 squared? 20. So then you can graph this. Right? I'm doing this a little quickly because we did this yesterday in terms of the class. So negative 1, negative 2, 1, 2, 1, 2, 3, 4, 5 is good. So negative 2 is 1/25. It's like really close to the x-axis. 1/5 is pretty damn close too. 5 to the 0 is 1. 5 to the first is 5. And then 5 squared is 25, way up there. Right. So then they all have this look to them like this. They all look like that, just the bigger the base is, the quicker it grows and the quicker it shrinks. So if you go this way, it actually models population growth. If you plotted the population growth of the U.S., it would roughly follow this curve. If you go this way, it's you guys, what happens to radioactive elements? What happens to them? Why do you not want to be near them? They decay. You know what that really means? They emit particles. Right? And that's why if we're near something radioactive, the particles are hitting us and some of them interact with their cells, and that's bad. That's a very bad thing. Just play a little Fallout and you'll find it. So that's, I just want you to throw, just to show you how the exponential function is stupid important. It models so many things really well. And why do we want things to model something? Because I want to be able to predict what's going to happen. When is Chernobyl going to be non-radioactive enough for people to live there? Well, thousands of years, actually, right? There's a stupid horror movie I didn't even want to watch. And when will the population of the Earth be too much? Well, we can kind of model it and go. And the models are different because they're using different possible situations, right? I don't know if you guys have ever heard of population growth, and we're worried about, are we all going to have to stand on each other's shoulders just to live here?
And 1 over 25 is supposed to be negative, right?
No, definitely not. No. Negative powers only do what? Flip things. So if I have 3 to the negative 1, that's 1/3. If I have negative 3 to the negative 1, what's that?
Oh.
What's a negative power do? What's it do? It just does what to something? Flips it. So this would be 1 over negative 3, which is negative 1/3. The only way you can have the answer come out negative is if it starts negative. Because what's the only thing a negative power does? It just flips it. So if it's a positive number, it's still going to be a positive number when you flip it, right? So a lot of people get confused about this negative sign. All that means is you have 2 5s on the bottom. That's all it means. That's all it can mean. Maybe. So what's the key thing about back here? What happens back here? Does this ever hit 0? No, because even if you put negative 18 billion, 5 to the negative 18 billion ain't 0. It's something really stupid close to 0, but it ain't 0. It's an asymptote. I like it. So this is asymptotic. Asymptotic. Old. Sorry. All right. Supersonic? No. Okay. So that was very quick, I know, and it had to be, because now I need to get into logarithms. And just to get into this, I know some of you guys are like, all right, time for me to just shut down, but what is the cube root of 64? 4. And so you got to be careful. 64 is evil, I know, because it's 8 if it's square root, it's 4 if it's cube root. Why?
Because 4 by 4 by 4.
And why are you thinking that way? Because you know the question that symbol is asking you. I know I'm making a big deal of something that you all know, but this is important because you all just know what that symbol means, so you don't even think about it. Like cube roots are easy, but logarithms are hard. Screw that. You just don't internalize what the log is asking you. So a lot of you guys might be new to logarithms. I don't know if some of you guys have never used logarithms before. I actually some of you guys, good. I'm kind of happy about that. Nice clean slate. The rest of you guys, maybe you learned some shit. So that's 4 because this wants to know what does it take 3 of to multiply by 64, right? We don't even say this to ourselves, but we just know that's what it means. How we doing? Yes. Second.
Section.
We're getting 12.3. Yes. So when I ask you something like this, and it's an unfortunate symbol. It's just a symbol. I know it's a word also, right? You know, like frogs are in logs. What the hell is this shit? Is this going to turn into some kind of weird Dr. Seuss poem thing? No. Logarithms, the word logarithmos is the study of numbers or something. I can't remember the Latin of it, but for some reason they picked that to be the symbol, and it kind of sucks. But oh well, too bad for us. I really want you to realize that didn't have to be the symbol for a cube root. A cube root could have been like this. Why not? That could mean, what does it take 3 up to make 64? And then we just have to make sure, hey, guess what? That means this, that means this. And then everybody goes, oh shit, I understand now. I don't know if you guys understand what I'm trying to say. The symbols we pick sometimes make it look like it's harder, but we just got to focus on what it's asking us. So if I said, what's log base 3 of 9? The question that is asking is, what power does the 3 need to make 9?
2.
It needs the second power. 3 squared is 9. So what question does a logarithm ask you? What power does the base need? See how that's down there? That's the base. What power does that base need to become this number? That's the question that a logarithm asks you. Is that a difficult question to answer? Sometimes, but most of the time, no, it's not. It's not a difficult question to answer. It's just that people don't understand that's what you want to focus on. What is it asking me to figure out? So, let me see you guys. That's all it is. That's it. What power does this need to become this? Or how many of these have to be multiplied to become this? Do you see how that's not the same thing as a square root or a cube root? It's not the same thing. Is it?
So the question on that isn't log 3, 9 equals 2. It's log 3, 9, and then we have to find out what it equals.
Yeah, I mean, this was blank when I started, right?
Okay, yeah.
And then we figured out what 3 to what power is 9, 3 to the second power is 9. So really, you're just asking yourself, if you see this, log base, let's associate something here, 464. What question are you asking yourself? What power does 4 need to become 64? What power does it need? 3 power. So I want you to really, there's a lot of similarities between roots and logarithms. But here I know the power is the third power. It's associated to the third power, right? What to the third power? 64. Whereas this, the unknown is what the power is. I don't know what the power is supposed to be here. I know what the base is. I just don't know what the power is. Do you see what I'm saying? So we need both functions to exist. We do, because they deal with different situations. So be real careful. It's not the same thing as a root. So what about this? Log base 3 of 81. We'll do several easy ones. Think about it.
3? Wait, no. It's again.
3 threes only makes...
It's going to be 3 to the radical of 3.
How many 3s? So what's the question? What's the question this is asking you?
To the fourth power?
True. What's the question this is asking you?
How many 3s is 81?
How many 3s multiplied would make 81? Or what power does 3 need to become 81? 4. 4 3s make 81, right? 3 3s only make 27. Multiply by one more 3. What's 3 to the fourth power?
So, like exponent?
The answer to a log will always be a power.
Yeah.
So the answer to a logarithm will always be a power. Because the question is, what power does this need? Okay, maybe.
I like the way how you worded that one better. How many 3s to equal 81?
Yeah, that's why I say things multiple ways. You never know which way it's going to stick.
So that's how you write the answer? That's what I write.
This would be the answer here, and this is an explanation of why. Right? This is the answer. This is just explaining why this is the answer.
On the test, when
You better put 4 here.
Okay.
Right? I can see this, but you better circle this.
Okay.
If you just say this, and I'm like, what's the answer then? You got to understand the answer is 4.
Okay.
So logarithms are powers. Right? They will always be powers. Why am I making a big deal out of that? Because we're going to talk about the properties of logarithms, and they're the same as the properties of powers. They're exactly the same. They have to be, because logs are freaking powers. Right? Freaking. Well, they technically term. Alright, so let's try some that aren't as obvious, but you still don't need calculators for it. Let me see if anyone gets this. Don't say anything out loud. That was a little bit harder, but not that bad. Think about it. Alright. Yes, ma'am.
Would it be -2?
Yes, cool. Why? If that wasn't there, the answer would be 2, because it takes 2 sevens to make 49. But I also have to flip it. So what kind of power makes that happen? A negative power. And how do you check yourself? You can always check yourself by doing this. That to that power has to equal this. And 7 to the negative 2 does equal 1 over 49. How are we doing? So don't let the log part of it throw you off. It's easy to let that throw you off, but it's just a symbol. They could have used a better symbol. They could have had an entirely different symbol, like a square root symbol, just different. Right? But they were like, let's use some Latin. They haven't used Latin in a while. Sure. Logarithms. Let's shorten it. Log. Yeah, I like that. Logs are easy. Oh, God. And then students just give up when they see this shit. They're like, well, now you're throwing whole words into this. What the hell? Yes.
So essentially it's saying 7 to the power of x equals...
Yes, good. So a different way to write this. At first I don't know what this is. So you can always rewrite a logarithm. So when I don't know what this is, I can call it x. And then you can rewrite this as 7 to the x equals 1 over 49. You can rewrite it if it helps you focus on what the question is. You guys see that? You can rewrite a logarithm as an exponential. You can rewrite an exponential as a logarithm. So real quick, on the heels of that, how would I write this? 8 to the y equals, you don't even know what the answer is, but it doesn't matter. How would I write that? This is harder to do. How would I write that as a logarithm?
Log
What's the base?
8.
8. What's the power?
7.
What's the power? Y. So why do I put the power over there? Because the log is a power. And then what's the only thing left down? Maybe let's just soak in. You have to be able to write them in both ways, right? So 8 to the y equals 7.2. You can check yourself that way. So it's easier to go from a log to an exponential because I can just see 7 to that power equals that. Bam! It's a little bit harder to go from exponential form to a logarithmic form. And I really want you to understand, all I'm doing right here is, what's another way to write this? You can write it as x equals, what's another way to write that?
X to the
7 to the
third.
Right? I mean, those are 2 different ways. I can write it in radical form or I can write the statement in power form. Right? They both represent the exact same idea. That's all I'm doing here is, this is in logarithmic form, this is in exponential form. That's all. It's the same question. Right? Yes, ma'am.
The last one that you did, log 8, 7.2. What? I'm confused with that one.
So it started here and I went to this. So what's the base here? What's the base?
What do you mean the base?
What's the base? So if I write x squared times x to the 5th, why are you allowed to do this? Why are you allowed to do that? Because the what are the same?
The not the exponents, the
The
base.
bases are the same. So what's the base?
The
8. 8's the base. What's the power?
Is that a y or a 4?
That's a y, right? So
Y.
the y goes over there because the log is a power. And then that output goes here. So 8 to the y equals 7.2. You can see that when you get to the end.
Oh, okay. So what we're doing, we're not solving this.
No, we're just
trying to-
rewriting it.
Okay.
Right? So that question is the same as that question. Right? I like it. This question, x to the 5th equals 11. What's another way to write that same question?
Log x.
No, not in logarithmic form. I mean in radical form. Radical form.
X equals to the root of 5.
5th root of 11. Right? Those are the same exact question. What does it take 5 of to multiply the 11? What does it take 5 of to multiply the 11? They mean the exact same thing. Just rewriting the same expression in 2 different ways. Maybe. Let's try one more of those. So if I had a to the m equals p. No numbers at all. Like, how do I write this in logarithmic form?
Log a.
Yeah, log base a, because that's the base, of p equals m. Because it takes m a's to multiply out to be p. Right? You can check yourself at the end. A to the m equals p. Check. That's what it says. Right? So what's kind of nifty is, what would you say the input is here? It's a little bit weird, but what would you say the input is there? It's hard to see on there. Let me do one more. Equals, what you got, Jen? Doesn't matter. Yeah. What would you say the input is there? What's the input?
For the X.
X is the input, right? If you put a 2 in, you get a 9 out, for example, right? So the input is X. What's the output? Y. So I've wanted to put it in more familiar terms. Here, the input would be M, the output would be P. Right? For every M I put in, I get a P out. So when I do this is kind of nifty. A logarithm is the opposite of an exponential. They're opposites of each other. I don't know if you realize this is what's happening. This tells me if I said 3 cubed is 27, that tells me I have 3 3s. But this way says, what do I need 3 of to make 27? They ask opposite questions. One gives you how many you've got. The other one asks you how many you need. They're opposites of each other. All right. So how do I write this in logarithmic form? What's the base?
Log base 3.
3
Of Y.
of y.
Equals X.
Do you see how the input is now the output? The output is now the input. Because they're opposites of each other. So when I input 4 into a square, I get 16, right? What do I put into the square root to get 4? 16. So here the input is 4, the output is 16. Here the input is 16, the output is 4. That's how opposite functions work. It's another way to remember what goes here and what goes there is the opposite. What was the output is now the input. What was the input is now the output. You can look at it like that if you want to. All right. So let me take a step back because I want to make sure we all really understand these logs by themselves. You got a little sidetrack there. Oh, let's see. My Roman numerals are getting way up there. What about this? What is log base 7 of 1? Don't say anything out loud. Think about it. Remember what the question is. Logs are hard because you actually have to remind yourself what the question is. Radicals are not that hard because you've been using them a lot longer. You've internalized what the question is. You don't have to think about it. All right? So poor logs get a bum rap. Yes?
Is it 0?
Beautiful. Because what are you asking yourself? What power does 7 need to become 1? What power does anything need to become 1?
0.
0. Except for 0, but you can't have... Hopefully you understand you can have a 0 in the base. You can't even have negatives in the base officially, but when you get further along, you can do all kinds of weird shit. Right? For right now, you're not going to see any negatives in the base. How are we doing so far? Do you understand what I'm trying to say? If you understand what the question is, then the symbol doesn't matter. The symbol they picked doesn't matter. They picked a horrible symbol. Right? Probably the same people that call imaginary numbers imaginary. Same bad team. Hopefully they broke them up and killed them. Maybe not killed them, but back then things were really rough. What about this? Whatcha? Ooh, I know. Log base 11 of 11 to the 7th. This is almost too easy to believe. It tells you the answer. And some of you guys are like, don't say shit like that to me. I don't know what the answer is. And you're saying it's easy. I feel bad now. I'm not blaming you too much here. Well, again, what's the question asking you? How many 11s do you need to make 11 to the 7th? You see how it's telling you the answer? How many 11s do you need to make 11 to the 7th? Well, you need 7 of them. So watch this. Another way. Does that make sense? That's telling you the answer. Another way to look at this is what log base 11 and 11 to the something power are opposite functions. So what should opposite functions do to each other? Kill each other. So you get 7. That's another way to look at it. You have to look at it either way? No, you can look at it the best way for yourself.
Wait, did you just cancel the 11?
The log base 11 and the 11 to the x. So this function is the opposite of this function. Gather. Those are opposites. Just the same way that this function is the opposite of that function. So what's the cube root of x cubed? What do these do? Cancel. Same way that these cancel. But do you have to look at it that way? No. You can just reason it out. You can just figure it out. You don't have to look at it that way. Stay with me now. Oh, look at that. We're up to 9. Cool. Let's see. Now just to help you out, remember the answer is always going to be the power required. But don't forget, what's like a 1/3 power really mean? What's a 1/3 power better known as? A what? A cube root. You with me? So the answer could be a root. Because then you can write it as a power, right? So what root would I do to 100 to make it become 10?
1/2.
A square root, a 1/2. I love it. So yes, the answer will be powers, but remember, we learn now that roots are powers. So I have to cut 100 in half multiplicatively to make 10, right? So it takes 1/2 of 100 would make 10 multiplicatively. What is 100 to the 1/2 power? Square root of 100? 10. Check. It checks. Alright, maybe. So what about this? Roman numeral F 10.
Professor,
Yes, sir.
do we have to show all that work when we do it?
No, this is me explaining.
Oh, okay.
So if you just do that, I'm okay. Thankfully, you don't have a log base 100 key on your calculator. In fact, most of you guys don't have a log on your calculator, I would think. Right, so that's good, actually, for me. Does anybody have a log on their calculator? It says log. That's understood to be log. Like when I write this, what's that understood to be?
Log 2.
No. What's this understood to be? The square root. When you just see log, that's understood to be the log base 10.
10.
Why would that be true? Because 10 is the basis of our number system, right? Square root is just because we use the square root the most. But when you hear Richter scale, we live in California, so Richter scale, that's a logarithmic scale. Oh yeah. So every jump, if I compare an earthquake of magnitude 4 versus an earthquake of magnitude 5, that's 10 times as powerful. Every jump is a jump of 10. Right? Oh yeah. So what's, alright, so what about this here? 7 to the log base 7 of b. Just to kind of give it away, what happened here? Exactly. Log base 11 and 11 to a power cancel. So 7 to a power and log base 7, they cancel. So the answer is B. They cancel each other. So what happens here? They cancel. What happens if I put the cube on the outside? Does something different happen? No, they still cancel. Anytime an opposite function acts on its function, it will kill it. I don't care if one's on the inside, one's on the outside, who cares? Another way to look at this. Nobody ever gets this, but I'm never going to give up on explaining it this way. Right? If you understand what I just said, beautiful, stick with that. But watch this. What does this represent? What does this represent? What would the answer have to be? It would have to be the number that does what? What does it have to be? What's this ask you?
How many times is...
How many 7s to multiply to make B? So the answer would be the power 7 needs to become B. Are you with me? I really want that to sink in. If you understand what I just said, you're really pretty good right now. You're at a good spot. So this represents the answer. Whatever the answer is, it would have to be what 7 is raised to make B. So what happens when I raise 7 to it? I get friggin' B. That's what it says. It's the power that 7 needs to become B. So when I raise 7 to it, it becomes B. Why? Because that's what the thing does. That's what this does. That's what its whole life is about, is to make 7 become B. If you don't like that way, I live that way personally, but you get, just B. All right, beautiful. That's perfect. Because they're opposite functions. Screw it. Kill them. Either way. How do you guys feel about logs? Anybody hated logs and now you're like tolerant of logs? I can tolerate them. I used to hate them, but it's okay. All right, maybe. All right. So let's do this. One last topic, and then that's the last new thing for the semester. That I'm going to make you responsible for homework. Let me be careful how I say that. And this would be section 12.4, properties of logarithms.
And you said that you're going to be kind of like lenient on the homework as far as if we turn it in after the test.
Oh, as long as you give it to me by the day of the final.
Okay.
Yes.
But don't you lose points?
Say again?
Don't you lose points that way?
I just said you would. That would be so evil. I basically said you would. Yeah, you can turn it in. What'd you say? No one will take points off. But again, I plead to you. Do examples out of every single section so you're ready for the test, right? And then you can finish up the rest for the day of the final, right? Don't just leave entire sections untouched, because then guess what? You're not going to have a clue what to do with them on the test.
One more question about homework. If you write like finish or complete, are you only giving us half credit?
Yes. So if I say correct or if I say finish, if anything's wrong with it, it's half credit. If I said redo, that's no credit, right? And you better redo it and if you do it well enough, I'll give you full credit again.
Okay.
So if anybody got anything that says redo or question marks, that's bad, right? That means no credit.
Incorrect means that it was correct? Or what?
Correct means correct mistakes.
Okay.
So do corrections to get back to full credit. You're at half credit. Do you have to do corrections? No. You can live at half credit if you want to. That's fine. It's up to you. All right. Yes, sir.
How do our homework stack against our quizzes? How do our homeworks go against
All right. So quizzes are 5% of your overall average, and the rest of that percentage is for homework.
Okay.
So you can work it out. I like it. No, I'm sorry. Turn that back around.
Yeah.
Homework is 5%, and the rest of it is
what?
Homework is 5%. Homework is 5%. Yes. Homework is 5%.
Yeah.
Totally
No. This is what I have to do. And real quick, just if I could, I would make homework do nothing. Do worth nothing, right? I did that one semester, and I'll never do it again because, of course, what happened was they're human. They're going to do the homework that's due. None of them did my homework, and they all failed the first test. So, well, that experiment went badly. But in reality, I wish I could do that because homework, if you don't do it, you're already screwing yourself over. So it's kind of evil to me to make homework worth something. You didn't do homework, so then you did bad on the test. Double whammy, right? Not only did you do bad on the test, I'm going to also give you lower homework grade. So I make homework worth something, but worth 5%. That still affects your grade decently much, but not crazy. You with me?
But it helped a lot of people when you show that graph.
Yeah? Okay, good. I should show that first day. But I like to show evidence from that class, so you can see it's not, well, that's your other class. That ain't us. It's every freaking class all the time. That line I showed you with the dots, I love it every damn time, right? All right, but if I make homework worth too much, people cheat, and then it actually affects your grade. If I make homework worth nothing, nobody does it. So I make homework worth very little. So if you cheat, you're still going to fail. And if you don't do the homework, you're going to fail, but you're not going to fail because the homework took you down. Kind of with me?
The tests are what? Tests and finals, in which?
The bulk of the points, yeah. Exactly. Your quizzes all together are like 15% or something like that. So that's a decent little chunk, but all right, that's enough. So help me out here, What does this represent? Let me do this. Log base 12 of 3. I'm not saying you should be able to answer the question, what is that, but what does it represent? What is it asking?
How many 12s does it take to go into 3?
Careful how you say it. It's how many 12s multiply to become 3.
Yeah.
Right? So some fractional answer, some root. You would take a root of 12 to make it become 3. What root? I don't know. Some weird-ass root. Right?
Wouldn't it be 1/4?
No. 1/4 times 12 is 3. This would be 12 to the 1/4 power. The fourth root of 12 is not 3.
You can't do that.
You totally can't.
We can't do that.
We can't do that. No. Yeah. But the answer, I really want you to get... If I put a 1 there, what's log base 12 of 1?
0.
0. I like it. Because 12 to the 0 equals 1. I like it. So every time you hit a log problem, especially your brand new logarithms, you've got to remind yourself what it's asking you before you put an answer down. Or else you're going to do stuff like divide, right? And that's not right. It's not division. Why would we make a whole new symbol that means something we already use a symbol for? We wouldn't do that. It's got to mean its own thing. So that would be 0. What's log base 12 of 12? 1. So what's log base 12 of 3? It's got to be something between... Yes, 0 between 0 and 1. And what's between 0 and 1? Some kind of root. Fractions are between 0 and 1, aren't they? True fractions, 1/12, 1/30. 1/8. All those are between 0 and 1. It's going to be some kind of a root. How are we doing so far? And again, that's more than I wanted to say with the actual answer to this. But what does this mean? This means the power that I put on 12 to make it become 3. Right?
Uh-huh.
What does this mean by itself?
12 times something equals
So this would be 12 to the x equals 3. That's what this by itself means. This would be 12 to the x equals... That's a 4, yeah, sorry. 12 to the x equals 4, right? That's what that would mean by itself, right?
Wait, so that's the answer?
No. We got to figure out now what happens when you add these together. So if that power makes 12 become 3, and that power makes 12 become 4.
It's 3 times 4.
Yes, that's true. Then you would multiply this to become 12. Sorry. Be log base 12 of 12. Now let's see if we can understand what I'm trying to figure out a new way to represent this so we don't have to go through the real technical proof. Because the real technical proof you get kind of lost in.
Basically.
True, but why?
The bases are the same?
The bases are the same. This is true. The bases are the same. But what do logs mean? They're powers, right?
Yeah.
Logs are powers. So if, what I'm really asking now, let me write this like this. 12 to the y, because it's not the same as this. Right? They're not the same. So what I'm really asking is, what's x plus y? What does it do to 12? Right? So if this power makes 12 become 3, and this power makes 12 become 4, then 12 to the x plus y, I'm going to try this. You guys, just stay with me. I got a nice little handout that summarizes what we're going to go over. This is weird because we're trying to figure out what it means. What does it mean when you add 2 logs together? Well, the power. So what does it mean when you add 2 powers together? When do you add powers? When you're multiplying. So that's what I was saying earlier. All the properties of logs have to be the same. So this is asking, what does x, the power that 12 needs to become 3, x, and the power that 12 needs to become 4, y, what happens when you add them? Well, this would be 12 to the x times 12 to the y. Let me stop there for a second. Do you guys see? Is that true? If I did that, what would I do with the powers? Add them. So it's the same thing here, right? We're almost there. We're almost there. And you guys are all like, what the freaking hell? But please, you guys, go with me for a second. Right? Is everybody cool? This is what I mean by you can analyze any logarithm statement by itself. Because you know what the question is. Is everybody cool with this being the power that 12 needs to become 3? Mm-hmm. All right. And this is the power that 12 needs. Let me call it y, because it's not the same thing as the other guy, right? They're not the same. So let me give it its own symbol. So that's the power that 12 needs to become 4. So what happens when you raise 12 to the sum of those? Well, that's 12 to the x. What is 12 to the x?
12x.
Well, no. What's 12 to the x? 3. And what's 12 to the y? 4. So what must x plus y be then? 12 to the what power is 12? 1. And what's log base 12 to 12? What power does 12 need to become 12? 1. Oh, shit. So kind of think about this. What I've done is I've broken the number 12 down into a part that's 3 and a part that's 4. So when I add them back together, I should get back to a whole 1. It's kind of weird.
So couldn't you just have
Yes.
the powers?
But what am I doing right now? What am I doing right now? I'm trying to explain why it works. Now, what is it that you just do? So I never will teach you, just do this. And if you didn't quite follow me here, at least I tried. But I want it to make some kind of sense as to why that is the rule, right? That it's not just because we can never say, let's just make multiply. Why not? Yeah, sure. It has to actually make sense, right? So this is the idea behind the shortcut. The shortcut now, and this is really funny when a student says, why do you do it that way? The other way you showed us is easier. I'm like, this is not a way. This is why the way works, right? So here's the actual way you would do this. If I had log base, what do you got, Jeff? I don't know, man. 40 of 8 plus log base 40 of 5.
You want.
I'm sorry, I'm going backwards.
Yeah,
Let's do this. Log base 40 of No, this is fine. This will work. My bad. How do you do that? When you add powers, logs are powers. So when do you add powers that have like bases when you were multiplying the two things, right? So this would be log base 40 of 8 times 5. Log base 40 of 40. Which is 1. So I took 140 and I broke it up into 8 and 5. So when I put those back together, I should get back to my 1. That's another kind of way to look at it. Why does this not make the most immediate sense? Because we're just learning logs, right? So we're not used to how they work yet. But we've got to keep reminding ourselves logarithms are just powers. So when do I add powers that have the same base? When I was multiplying. That's when I would add them. Yes, ma'am?
Are you going to show us one where the bases are different? Or
Well, it's sort of like me asking you what's the cube root of x plus the fourth root of x. Can you do that? No, they're not like terms. So you see, I could write a problem like that, but that's... So if I had log base 7 of 2 plus log base 9 of 3... Right, well, I mean, you can actually do something there, but log base 9 of 7, there you go. Ain't a damn thing you can do. You can't make it log base 16 of 4 or some weirdness. So the only way that you add the powers when you multiply like bases, which means these have to be the same, because those are the bases. So what do you think about this? Don't worry, I got it. Stay with me. We're just talking about ideas right now. Log base 10 of 20 minus log base 10 of 2. When do you subtract powers? When you were doing what? Dividing. So how can I rewrite this as log base 10 of 20 divided by 2? Which is log base 10 of 10, which is 1. Yay.
So how would we write the answer just for that one? Like log base 40 over 40?
This would be how you would write the answer. That's the answer.
Oh, so you write the answer as just 1.
Yeah, in this case, you can actually figure it out. There might be some situations where there's letters in there, you can't figure it out. You just put them together. But this one is actually, I could do log base 40 of 40.
So when we're adding, we're multiplying, when we're subtracting, we're dividing.
Exactly, because when you divide like bases, what do you do with the powers? When you divide like bases, what do you do with the powers? Subtract. So this is just saying the same thing. When I divide things with the same base, I subtract the powers. That's what that says. Do you guys understand? Okay. And real quick, a concrete example here. These are actually not concrete examples. What do I mean by concrete example? I mean something like this. Log base 100 divided by 10. There's 2 ways to do that now. I could do this property we just learned. Log base, let me go ahead and put it there, 10. Normally I won't put the 10 there. Right? So like not putting the 2 in the square root, but I'll do it for right now. Log base 10 of 100 minus...
Gross.
Really gross.
It was like stuck
Let
in my
the math be
throat.
gross.